All right, chemistry class, welcome to another session here. We are looking at chapter 8 in this video, and you're going to start to realize that all the things that you've been learning before about chemical formulas, chemical compounds, atoms, valence electrons, all that, they're going to start to come together here, and everything is going to really be used in order for us to move forward. So I highly encourage you to make sure you understand all the previous 7 chapters, and if you have questions, please let me know, okay? We are talking about chemical equations and reactions. Now remember, in our last chapter, chapter 7, we talked about chemical compounds and their formulas. So we're going to be using those formulas today in writing a chemical reaction, the equation for a chemical reaction. Okay? All right. If you would, you can pause the video and answer these 2 questions. It just helps you to think about what we've learned and where we're going today with that knowledge. So pause, answer these 2 questions in your notebook, and that I should see when I check your notebook. Okay, let's talk a little bit about a chemical reaction and how we're going to describe it. Now basically, let me just explain what happens here is you've got atoms, compounds that basically are going to collide with each other, and through that collision, the energy of that collision, there is going to be the possibility of bonds being broken. So bonds like in compounds, when we talked about ionic bonds and covalent bonds, those bonds are going to be broken, and the atoms are going to rearrange themselves and form new bonds and new compounds as a result of the chemical reaction. Okay? Energy is needed for these reactions to occur. Sometimes we're going to have energy put into the system. Energy needs to be put into the system, and we'll talk about that. And sometimes when energy is put into the system, more energy is given out, and we'll talk about that as well. So it does involve energy to break those bonds. Remember, we talked about bond energy, and then new bonds are formed, and usually when new bonds are formed, energy is released. So we'll talk about the difference between the energy that needed to break those bonds and the energy that's released when we form those bonds in a later chapter. When you have things colliding, the things that are colliding, the things that are originally before the reaction, we're going to call those reactants. And what you produce afterwards, after the reaction, those are your products. Okay? Please write this down in your notes. A chemical reaction is basically a way that we are going to demonstrate what is happening at the molecular level, what's happening with these molecules and compounds and atoms. It's a way of showing the results of a chemical reaction using symbols and formulas. Remember, we talked about those formulas before. So here's an example. If there is a reaction, let's say this reaction is happening right here. This is ammonium dichromate. If you remember, this is a polyatomic ion right there, and here's another polyatomic ion. And that S right there tells us it is a solid. This is a solid, and this is our ionic compound, 2 polyatomic ions. So we have 1 part ammonium dichromate. You know it's 1 part because it's not written, but there could be a 1 in front of this. That means you've got 1 of these molecules. Okay, ionic compounds, basically not a molecule, an ionic compound. So you got 1 of these compounds. Okay, then what happens is through some process, some reaction, something happens to this, and it's going to break apart. And this arrow tells us that something is going to happen. So this is before, and all of this is after the reaction over here. So before, on the left of the arrow is before, on the right of the arrow is after. So we sometimes say yields. In other words, this reaction yields something on the product side. Well, what happens? You'll notice that we have nitrogen in the original compound, and we've got a nitrogen over here. We have chromium, and here's some chromium, there's oxygen, here's some hydrogen, there's some hydrogen, some more oxygen. So we're not going to lose the atoms. All they're doing is rearranging themselves to form new compounds or separate themselves into elements, as is the case here with the nitrogen. So you'll notice that we still have all of the same stuff, it's just been rearranged, and we call that a chemical reaction. When you produce something new, you definitely have had a chemical change, a chemical reaction has occurred, okay? And you'll notice that we have 1 part nitrogen. Again, there's no 1 written, but we could put a 1 right there. And we're going to produce 1 part chromium-3 oxide. Could be a 1 right there. Notice the naming here. This is chromium. This is oxygen. And it looks like from the subscripts there, this is chromium-3. Chromium-3. And oxygen always forms a 2 negative. This is a metal and non-metal. That's ionic. And to form this compound, you would have 3 parts oxygen to 2 parts chromium. That's why the formula is the way it is. Okay? And then you've got your water over here. And notice we have 4 parts water. Okay? 4 parts water. The 4 in front tells us how many we have. I mentioned already this S means it's a solid. The G means it's a gas. There's solid, there's gas. If you see an L in parentheses, that means it is a liquid. Okay? And one more, if you see AQ, it means it's dissolved in water. It's called aqueous. Aqueous. Okay? Aqueous. All right. As mentioned, there's your reactant. There's just 1 reactant, and here are your 3 products. So just be aware of that. Now, when you have a chemical reaction, there are some ways that you can make an observation and you can say, hey, I wonder if a chemical reaction really occurred, because sometimes we can't really see what's going on, obviously. So there are some indicators that we look for, some observations that we can make to maybe give us a clue whether a chemical reaction is occurring or not. It's not a guarantee, but many times these indicators are good clues that a chemical reaction is occurring. 1, if energy is released. If during the reaction the container maybe feels warm, or you take the temperature of the solution, for example, if the reaction is happening in the solution and the temperature is going up, then energy is being released. Energy is being released. That's a good indicator that a chemical reaction has occurred. Now that energy release could be in the form of heat. It could also be in the form of light. So if you see light, there's a flame or something like that, or sparks, that's probably also a good indicator that a chemical reaction has occurred. If a gas forms, if you see bubbles during your reaction, that's a good indicator that there has been a chemical reaction. Okay? If you see a precipitate, and a precipitate is simply a solid that is formed when you mix 2 solutions. So over here you can see that there's a solution that's being poured into another solution, and this cloudy substance actually is a solid. That's a solid that is forming as a result of the chemical reaction that is occurring between these 2 substances. So that solid is called a precipitate. Okay? There might be a color change. So if you mix 2 solutions, or maybe something burns, or whatever the case may be, often a color change is a good indicator that there's a chemical reaction. Not a guarantee, but it's a good indicator. Okay? Now, please understand, I'm going to say this again. Observing these signs, and by these signs I mean these 4 things right up here, observing these signs only means that a chemical change possibly occurred. Possibly. It's not a guarantee. Possibly. Many of these signs also occurred during just a physical change. Remember, a physical change, there is no change in the chemical composition, the chemical makeup. Okay? So like boiling water creates a gas, you see bubbles, but that's not a chemical change, that's a physical change. Okay? The only guarantee that you have on whether a chemical change has occurred or not is if you create something new product, and you test it and it has totally different properties as compared to the reactants over here. Okay? So if you form something new, it should have new properties, it should be a new chemical composition. That's the only way you really can guarantee. But we do make some observations, as I mentioned: energy release, gas formation, precipitate, and color change. Okay, let's talk a little bit about chemical reactions must satisfy the law of conservation of mass. Now, we've mentioned the law of conservation of mass before, but now we're actually going to practice it. We're going to see it play out in our chemical reactions, okay? There's a couple things that you must do when forming or writing a chemical equation. One, it has to be factual, so we have to make sure that we show all the reactants and products and we don't leave something out, okay? It must contain the correct formulas for the reactants and products. We can't just make up stuff. We have to make sure that we have the correct formulas, and that's the lesson previously from lesson 7. We worked on writing chemical formulas, okay? And we must satisfy the law of conservation. So if there are two oxygen atoms that react, then after the reaction we have to show that there are two oxygen atoms. Okay, nothing is going to disappear or magically appear. We have to observe the law of conservation of mass. All right. Now, to do that, this part right here, ladies and gentlemen, to make sure that we satisfy the law of conservation of mass, we can't change a formula once we have made it. Once the formula is made correctly, we can't change the subscripts. What we do to balance this law of conservation of mass is we put coefficients, the big number. This is a coefficient, the big number right there. Okay? So if water is in our reaction, and on one side of the reaction, I'll just give you a quick example here. Okay? Let's say that water breaks apart into oxygen and hydrogen gases. So hydrogen and oxygen gas. Hydrogen and oxygen gas are diatomic, so they always appear in nature as H2 and O2. But water is H2O. Now, is this balanced? Well, let's see. On this side, on the reactant side, I have 2 atoms of hydrogen in the water. And over here, I've got 2 atoms of hydrogen bonded together to make hydrogen gas. Yeah, 2 on one side, 2 on the other side. Great. What about oxygen? In the water, there's only 1 atom of oxygen. But over here, somehow, what? There are 2 atoms of oxygen to make this oxygen gas diatomic. Well, somehow we have to correct this. We have to make it right so that oxygen just isn't magically appearing to make this O2. And you cannot, listen carefully, to fix it, you cannot put a 2 right here for oxygen. This now is a completely different compound. That's not H2O anymore. You just made hydrogen peroxide. That's H2O has to stay H2O. You cannot change the formula. What we do is we put coefficients in front to change how many of those molecules are reacting. So what we do, look, if I have water on this side and I need 2 oxygens over here, then I need to double the number of water molecules. That doubles everything in this formula, in the water formula. So now I have 2 waters. I'll write it like this. It's like this. 2 water molecules coming together to form my hydrogen and my oxygen. Now, do I have the correct number on both sides? I've got 2 oxygens, and here I have 2 oxygens. All right, good. Now they're equal on both sides. But I also now just changed the hydrogens. 2, 3, 4. I've got 4 hydrogens, only 2 on this side. Well, all I do is I just double this guy. So really, this is what my formula looks like, my chemical reaction. It's a water molecule combining with another water molecule to form 2 hydrogen molecules and 1 hydrogen molecule, or oxygen molecule. 2 hydrogens and 1 oxygen. That's what's really happening. We don't write them all separate like that, though. We write them like this. There are 2 waters, so I put a coefficient of 2 in front of the water. There are 2 hydrogens, so I put a 2 in front of that. And there's 1 oxygen, and that is your balanced equation right there. I'm using coefficients, not changing the formula. Never change the formula once you have it set. Once you have the correct formula for water, the correct formula for hydrogen and oxygen, you can't change those anymore. You can only write coefficients, changing the number of each of them in order to balance. Okay? Now, I mentioned that there are some gases that are diatomic. You have to know these. So when you write hydrogen, just hydrogen, I'm not talking about hydrogen in a compound. I'm saying hydrogen all by itself as a gas. In nature, it always appears as H2. Same thing with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those 7 right there are diatomic, and you need to be aware of that. So if I know that oxygen gas is created all by itself, I don't just write O, it's O2 always. If chlorine gas is produced, it is always Cl2 by itself, never Cl by itself. Okay? All right. In addition to showing a formula equation, we can also use words to describe what's happening. Okay? So, for example, we can say methane, that by the way is CH4 I believe, plus oxygen, O2, yields carbon dioxide, CO2, plus water. Okay? Now, let's just do something really quick here. Actually, I'll save it for later. We'll balance later on. We'll practice balancing. But this is just to show that we can use words here in order to express a chemical reaction. And you should be able to take the words, now you may not know what methane is, but you should be able to take the words and transfer them to chemical formulas and then be able to balance it. That's what we're going to be doing soon. Okay? So we have a word equation, and we also have a formula equation. You should be able to do both, and given the words, you should be able to write the formulas. Given the formulas, you should be able to write the words. Okay? So basically, here's what is happening in our reaction that was just described. We have methane reacting with oxygen to produce or yield carbon dioxide and water. Or if you want the proper name for that, that is dihydrogen monoxide, right? Or we'll just say water. Okay, now let's look at see what's happening here, because we're going to balance this in just a little bit. You have 1, 2, 3, 4 hydrogens over here. On this side, we only have 1, 2. So we're going to have to do something in order to balance the number of hydrogens there. Okay? So what you probably want to do in this situation is leave hydrogen and oxygen until last. That's my suggestion to you. So let's first look at anything that's not hydrogen and oxygen. Here we got a carbon. We got 1 carbon here. Oh, we got 1 carbon there. We're good. Okay, we got 1 carbon on either side. So the carbons, let's just do this, reactant side and product side. 1 carbon, 1 carbon. Okay, I'm trying to keep track of them, to conserve them. Let's look at the hydrogens. I've got 4 hydrogens as mentioned on the reactant side, and on the product side I only have 2. So I'm going to have to double or triple or do something to this water to make sure I have the same on both sides. Well, I'm going to double them. Remember, don't change the water formula. Only put a coefficient in front. I'm doubling the number of water molecules. I'm not changing the formula. So I've got 2 water molecules over here. So that changes my number of hydrogens from 2 to 4. Okay? Now let's check the oxygen. I've got 2 oxygen on this side. And I've got 1, 2, 3, 4. Here's 2 right here. Here's 2 oxygens. 1, 2. And I doubled. I now have another water molecule here, okay? All right, there's my other water molecule. So here's my oxygen and another oxygen. I have 2 oxygens here, and I've got 2 oxygens here for a total of 4 oxygens on this side. Well, then I'm going to have to do something on the reactant side. I'm going to have to put a coefficient in front of this in order to have another oxygen model here, or oxygen molecule there. Now I've got 4. So little by little, you've got to balance this equation by changing the coefficients only. Only. Never change the formulas. Only the coefficients, and you might have to change them a couple times and just work back and forth until you've got the same number of each atom on both sides. This is the one that we just did, okay? So remember how we did that, and we'll have some more practice in a little bit here. And if you want to kind of create a table for yourself, and this is where you can kind of write down the number of carbon atoms on the reactant side, number on the product side, and just keep changing them a little bit until you have the same on both sides, okay? And here's the model that is actually happening. Originally, you see, originally the model was just showing one molecule of each of these. But in actuality, what has to happen in order for this to be proper and to be conserving matter and mass, you have to have one of these, two of the oxygens, one of the carbon dioxide, and two water molecules. Then there's your two water molecules. Then you have the same number of atoms of each element on both sides. 1, 2, 3, 4 oxygens. Here they are. 1, 2, 3, 4. One carbon, one carbon, one carbon. And our four hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. Kind of cool. It works out. All right. All right, as mentioned, a couple of things in our chemical equation, some symbols. This arrow means it yields. We're going to see a double arrow later on, and that means actually reaction is going to go both directions. You can create things going one direction and create things going the other direction. We'll talk about that later. S, small s in parentheses, means that that particular compound is a solid. This downward arrow means that it's forming a precipitate. Okay, I don't see that very often. Usually we just write an S there to show it's a solid. L means liquid, AQ means aqueous, it's dissolved in water, G means it's a gas, and then this upward arrow shows that it's a gas, but usually I just see the G. I don't see the upward arrow very much. This arrow here, which means yield, sometimes you'll see a triangle above it, delta, or you might see the word heat, and that just means that there is a change in heat. There is heat as being put into the reaction. Okay? This is showing you under what pressure the reaction is occurring. If you see 2 atm, atm is a measurement of pressure. Okay? Or you could just write here, the pressure at which reaction is carried out exceeds normal atmospheric pressure. Okay? It just means that there's pressure going on greater than what would normally occur in the room or in the atmosphere. Okay? You might see an actual temperature, just telling you what temperature it is reacting at, or you might see a formula, and that means that this particular compound is called a catalyst. What that means is it's helping the reaction. It's not going to be used in the reaction, or I should say consumed in the reaction. It's not going to be a part of the products. It's just kind of helping the whole thing take place. That's called a catalyst. We'll talk about that more later on. Okay. Let's go ahead and, let's tackle this guy right here as an example. All right. We are going to write the words and the formulas for this following reaction. All right. So it says sodium oxide and water yield sodium hydroxide. So we have to think about our formulas now. We should be able to write the formula for sodium oxide. Sodium is in group 1 and it forms a +1 ion. It is a metal. It's in group 1. Find it on the periodic table. Oxygen, oxide, always forms a 2 negative. Metal and non-metals got to form an ionic compound. So sodium oxide, how many of each do I need? I need 2 sodium, 1 oxygen. So the formula for sodium oxide is Na2O. So you have to write the correct formula first. Okay? Then we got water, that's H2O, you should know that. And then sodium, there's that metal again, sodium, and hydroxide is a polyatomic ion. You've got to recognize hydroxide. Look on the table of polyatomic ions, it's there for you, it is OH negative. OH negative. Sodium is always a +1. So how is the formula going to be written? Just one of each. One of these and one of those. Okay? Now, here is the equation or the reaction written with the correct formulas. There's sodium oxide, there's water, there's sodium hydroxide. But we have to check to see if this is balanced. It may not be balanced. We might need multiple of these in order for the reaction to occur properly. So we test, we look at it. We look at this and we see that sodium, I'm going to start with anything that's not hydrogen or oxygen right now. Sodium, there are 2 of them on this side. I'm going to make a little table. 2 sodium on this side, only 1 sodium on the other side. There's one of these, two there. So I'm going to put a 2 in front of this entire compound, the sodium hydroxide. Why? Because I need to double the sodium. But I can't double it by changing the formula. You can't just put a 2 there for sodium. No, 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 no. That changes that whole formula. You can only double something by putting a coefficient in front of it once you have the correct formula. So now I just wrote 2, which means I have 2 of these. I have 2 of these NaOHs in the reaction being produced. That just doubled my sodium. I'm going to double my sodium just like that. Okay? Now let's look at the hydrogen. I've got 2 hydrogen on this side. They're both in a single water molecule. 2 hydrogens. Over here, I've got a hydrogen here in this sodium hydroxide compound, but I've got 2 of them. So it's like having 2 of these, right? It's doubled. There are 2 of them. There they are. 1, 2. There's 2 hydrogens. That's the same thing as writing a coefficient in front. You're doubling that compound right there. Okay? There's 1, there's 2. So I've got 2 hydrogens on the other side as well. The hydrogens are fine. Let's look at the oxygens. I got 1 here and 1 there. What about on the other side? I have 1 in the compound, but that compound is doubled. So I've got 2 oxygens and 2 oxygens, and everything is fine. All I had to do is put a 2 in front of that sodium hydroxide. Okay? Okay. Let's do one more here for some practice. It says write word and balanced chemical equations for the following reaction. Include symbols for the physical states. That would be S, L, or G. Okay, we'll do our best with that. There might even be some clues in the words there. Solid, there it is, solid. We're going to put an S. Aluminum metal reacts with aqueous, there's AQ, zinc chloride to produce solid, S, zinc metal, and aqueous aluminum chloride. So you'll notice it says aluminum metal. That is an element all by itself. Okay, so I'm going to write down Al, solid. It's all by itself. It's not an ion. It's not in a compound. It is all by itself. Just pure aluminum. Reacts, there's our arrow, with what? Zinc chloride. Now we got to think about how do we form the formula for zinc chloride. Well, zinc is a metal. Chlorine is a nonmetal. That's going to form an ionic bond. Zinc, I believe, forms a +1 ion. You can look on the chart, okay? Chlorine forms a -1 chloride ion. So you're just going to have one of each of these in order to make the compound, zinc chloride. That is the correct formula for zinc chloride. So ZnCl. And it's aqueous, so AQ. Okay? What is going to else? Oh, sorry. I'm sorry. It reacts with this. It doesn't produce this. I apologize. This is a plus sign here. Plus sign, okay? All right. Now we're going to produce. There we go. Now we put our arrow in. Okay, we're going to produce solid zinc metal. This is zinc, just zinc all by itself, solid. And what? Aqueous aluminum chloride. Aluminum chloride. Now aluminum forms a 3+. Okay? Aluminum forms a 3+. Chloride is a -1. So I'm going to need 3 of those there. So let's see if this works out. Yep, we can do this. Aluminum and chloride. So we're going to need 1 of the aluminums and 3 of the chloride. It's AlCl3. Okay? There's your solid aluminum. There's your zinc chloride. There's your zinc metal. There's your aluminum chloride. We have to write the correct formulas first. Now we're going to balance. Okay? Do I have the same number of aluminums on both sides? 1 aluminum here, 1 aluminum there. Yep, aluminums check out. How about the number of zincs? Yep, 1 zinc and 1 zinc. The problem is when I get to chlorine. I've got 1 on this side, I have 3 over here. So I'm going to have to triple this compound. Don't put a 3 on this zinc chloride. Don't put a 3 here. No, that's changing the formula. That is not the correct formula for zinc chloride. Put a 3 in front. What does that change? Yes, it changes the number of chlorines and the number of zincs. So I have now 3 chlorine atoms on both sides, but I just changed the number of zincs. So I need to also change the number of zincs over here, and I do that easily because it's by itself. So my final formula here with the physical states is this right here. Okay? And this is aqueous, I believe. AQ. So that is aluminum metal reacting with zinc chloride, a solution that has zinc chloride in it, forming zinc metal and aluminum chloride. Okay? This actually would go in my balanced equation box right there. All right? All right, we'll do some more in a little bit, and we'll keep practicing this, and we'll do some more here with some models as well. Okay? All right, let's practice this one right here. This is practice problem G. And first it says translate the following chemical equations into sentences. And then we're also going to check to see how they balanced it. All right? So let's look at this one. We have 2 nonmetals, carbon and sulfur. Carbon and sulfur, 2 nonmetals, which means it is a molecule covalently bonded. So we use prefixes. So this is carbon, 2 sulfur. So disulfide, ends in IDE, and there's 2 of them. Reacts, or you can say plus oxygen, or reacts with oxygen. Remember, oxygen is diatomic. That's why there are 2, O2. Produces, or you could say yields, produces what? This is carbon is a nonmetal, oxygen is a nonmetal. 2 nonmetals. Use prefixes. Produces carbon dioxide and this is nonmetal and another nonmetal. Sulfur and oxygen. Use prefixes. Sulfur dioxide. Okay? Now, if you wanted to get really specific, you could say 1 molecule of carbon disulfide reacts with 3 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of sulfur dioxide. You could also say these prefixes can mean molecules, but they also can mean moles of molecules. So this could be a mole of carbon disulfide plus 3 moles of oxygen plus, or yields 1 mole of carbon dioxide and 2 moles of sulfur dioxide. Okay? All right, let's do one more here. This is a metal and a nonmetal. That is an ionic compound. This is sodium. You do not need prefixes with ionic. Don't use prefixes with a metal and nonmetal. Sodium chloride reacts with, now you could say a solution, because this is aqueous, a solution of sodium chloride reacts with a solution of silver. Now this you have to recognize as a polyatomic ion, NO3, silver, just look it up, nitrate, nitrate. Yields or produces what? Here's another, metal and a polyatomic ion, sodium nitrate. And silver chloride. You do not use prefixes in this case. All of these are ionic compounds, metal and nonmetals, metal and nonmetals. Okay? All right. Now, let's again talk a little bit more about balancing equations and making sure that we understand that completely. Chemical equations show relative amounts, masses, and progression of chemical reactions. So let's just walk through this. First thing, as we mentioned before, the coefficient will tell you the relative amounts of reactants and products. It's kind of telling you how many of these molecules react with how many of these molecules. to produce how many of the product molecules. It's telling you kind of how, in what ratio they're going to react and combine. The molecules. I'm not talking about the formula right now. I'm talking about the molecules. So this is right here saying when you have hydrogen gas reacting with chlorine gas and it produces 2 molecules of hydrogen chloride. 2 molecules of hydrogen chloride. You have basically these coefficients are telling you the ratios in which they combine, or kind of the relative amounts. You have 1 hydrogen. This is 1 molecule of hydrogen right there, and 1 molecule of chlorine right there. Chlorine is diatomic, as is hydrogen. When they react, they produce hydrogen chloride right here, but you're going to produce 2 of them because you've got 1, 2 hydrogens, and there's your 1, 2 hydrogens. You got 1, 2 chlorine atoms, there are your 1, 2 chlorine atoms. So this is 1 molecule of hydrogen plus 1 molecule of chlorine produces 2 molecules of hydrochloric acid, or hydrogen chloride. Okay, maybe it's acid. This is aqueous. It's actually going to be an acid. We'll talk about that later. Now this could also be, it could be moles, as I mentioned before. These coefficients can represent molecules or moles. It could be 1 mole of hydrogen gas plus 1 mole of chlorine gas produces 2 moles of the hydrochloric acid. Okay? Or we could look at masses. Well, the mass of 1 mole of H2 is 2 grams because each hydrogen has a molar mass of 1. Here, each chlorine is about 35, so if you got Cl2 together, that's about 70 grams for a mole of chlorine. And here, HCl, each HCl has a molar mass of 36. That's the chlorine plus the hydrogen. 35 plus about 1, that's about 36. But there are 2 of them, so times 2 is 72.92. Now look here. Here's the conservation of mass. You're keeping the number of hydrogen atoms the same on both sides. The number of chlorine atoms the same on both sides. And that means the mass is conserved, conservation of mass. You've got a total of 72, about 73 almost, 73 grams of material over here, and 73 grams of matter on that side as well. Law of conservation of mass. Okay? The relative masses of the reactants and products of a chemical reaction can be determined from the reactions coefficients. Okay, again, that's just showing you exactly what we did up here, that the masses are conserved. Okay, and we can look at it individually, but notice that here we're using the coefficients. These are the coefficients right there for each of the molecules, multiplied by the respective molar mass to give you the total mass of the reactants. These are the reactants over here, and then the total mass of the products. And these two, the reactants added together, is going to give you the same as the products. Okay? Or product, there's just one. Now, we're going to talk in the future about reverse reactions. If you reverse the reaction for a chemical equation, it has the same relative amounts of substances as the forward reaction. Okay? In other words, sometimes reactions can go both ways. You see this double arrow right here? So nothing changes. It's just that when you have the arrow pointing from left to right, it means the hydrogen gas and the chlorine gas are turned into HCl. The arrow back to the other way means also the HCl can break back apart into hydrogen gas and chlorine gas. Both directions are possible. Okay? Alright. Chemical equations can be balanced with step-by-step inspection. So again, let's practice a little bit more on just balancing the chemical equation, writing it out in words, writing the formulas, and then balancing it. There's a step-by-step process here that I definitely want you to be able to master. Okay? So let's look at these steps here. If you follow these steps, you'll be guaranteed to have a balanced equation every single time. Okay? So the first thing here is we want to identify what the reactants are and what the products are. So in this one, in our example right here, it says water yields hydrogen and oxygen. From there, from that spot, you then have to write the correct formula. You can't make up the formula. You have to write the correct formula for water, H2O. The correct formula for hydrogen gas, it's H2, it's diatomic. And the correct formula for oxygen, it is O2, it's diatomic. Notice, once you write the formulas, you're not guaranteed that you're done. You may be, it may be balanced, but you then have to check. So we check. There are 2 hydrogens on both sides, we're okay. But the oxygens, there's 1 on the left and there are 2 on the right. So we have to double whatever has the oxygen on the left. I have to double that. I have to double the number of waters. Well, that also doubles the number of hydrogens on the left. Now I have 4, so I have to put a 2 in front of the hydrogen to get 4 on the right as well. This is your balanced equation. You have to make sure that you've got the same number of each element on both sides of the reaction. Okay? If you need to, you just count up, just make sure you got the same on both sides. We have 4 hydrogens. We have 2 oxygens on the left. We have 4 hydrogens and 2 oxygens on the right. Check. Okay? There are more great examples here in this chapter, so if you want to open up that chapter, the PDF file, and look through the different examples, I would highly recommend that. Okay? Alright, that concludes 8.1. Let's look at different types of chemical reactions. And what I mean by that is there's kind of some patterns that we can observe for certain types of reactions. And I'm just going to point out the main types of chemical reactions. These are all going to be chemical reactions, but we break them into maybe 4 or 5 different types. We're going to have 5, I guess, here. So one is synthesis, and I'll just mention that synthesis means you are combining something. Combine. Okay? Decomposition means you break it apart. Single displacement means that there's one element that's replacing another. Double displacement means there is one element and another element and they switch places. We'll talk about that. Combustion means something is burning in the presence of oxygen. There has to be oxygen involved. Okay? So let's look at some quick examples here. Synthesis. You have to write this down in your notes. I should see synthesis as one of the types. It says 2 or more substances combine. Combine, combine, combine. So here's the clue. If you see on the the left side, the reactants, if you see more than one thing, and then on the right side, on the product side, there's only one thing, that is definitely a synthesis. So you've got some element A combining with some element or compound, could be an element or compound, X. These are just general letters, and they're going to combine to give you one compound on the product side. That is a synthesis. Okay? Here's some examples. If you've got magnesium and you were to kind of burn magnesium in the presence of oxygen, like is happening right here, then you would create magnesium oxide. This is synthesis. Synthesizing means combining. So magnesium and oxygen are combining to give you magnesium oxide. Okay? Here's some others. Iron and oxygen combining to give you iron oxide. That's iron 2 oxide. And here, iron and oxygen combine to give me iron 3 oxide. Okay? But those are also synthesis reactions. And there's some more there, and you can look at them. But the key point is you have 2 or more things as reactants combining to give you only one product. One product. Okay, let's look at some others here. Let's look at the other type. And they give me lots of types here, synthesis reactions with oxides, etc., etc. And we'll see lots of reactions so we can practice them as we move forward. Okay? Another type, the second type here is decomposition. And this is kind of the opposite of synthesis. This is when you have only one reactant and it's going to break apart into 2 or more products. Okay? So one reactant, and now you've got 2 or more products on the right side. Here's some examples. Water can break apart into hydrogen and oxygen gas. That is a decomposition. One reactant breaking apart into 2 or more products. Okay? Here we have mercury oxide. breaking apart into mercury and oxygen. And now you're going to give a bunch of examples here. Here's the decomposition of metals that have carbonate in them. Here's decomposition of metals that have hydroxide in them. I'll give you some examples, okay? These are all decomposition. You can see one is breaking into two or more, okay? All right, single displacement. Single displacement is exactly the way it sounds. There's a displacement or replacement, sometimes you say, and it's just one thing is replacing something else. So this is a general form. You're going to usually have a single element, A, whatever that A is, and then you're going to have a compound here, B, combined with X. And when you compare the reactants to the products, you'll notice that A and B basically switch places. A kicks B out, and now A is in the compound, and B is by itself. Okay? Or here, again, Y, whatever Y is, I don't know, and it comes in here and it replaces, it's going to replace X. This time it's replacing the non-metal probably. It's going to kick the X out, and now you're going to have B, Y, and X is by itself. So basically it's like, you know, somebody comes in and kicks something else out, and now it's by itself. All right? That's basically the form that you're looking for. Here's an example. Here's aluminum solid all by itself, and it comes across lead nitrate in solution. When you put that aluminum into this solution, what it does is it's more reactive than the lead, and so it is going to kick that lead out. It's going to kick the lead out, and now it's going to be in this compound with the nitrate. So aluminum comes in here, and now it is going to be in the compound. There's your aluminum, and the lead gets kicked out all by itself, and there's your lead by itself. That's a single element kicks out another element. In this case, a metal kicks out a metal. All right? It can also be, in this case, now this one doesn't look like there is displacement, but if I write water, instead of H2, if I write it HOH, there's still two hydrogens and one oxygen. Here is your hydrogen, and the sodium is going to come and kick out that hydrogen. So now the hydrogen is going to be all by itself, and the sodium is going to be in a compound with the hydroxide. So this is sodium kicking out hydrogen. Here, iron is going to kick out the hydrogen. The hydrogen is going to be by itself, and you're going to have iron oxide. Okay? And you can see this is actually an example of that. Here you're putting magnesium, a metal. This is magnesium in HCl. It's going to kick out the H. The H is going to be all by itself, and now the magnesium chloride is in that solution. And here you can see the bubbles. That's your hydrogen gas that is being basically kicked out of its compound here. Okay? And you got hydrogen gas bubbles here. You can also kick out a nonmetal. So this nonmetal chlorine is going to kick out the other nonmetal. It'll never kick out a metal. A metal kicks out a metal. A nonmetal kicks out another nonmetal. So this chlorine can kick out the bromine. Now you've got the chlorine in the compound, and the bromine's by itself. Okay? All right. Let's look at, this is another example of a nonmetal kicking out another nonmetal. Double displacement. Double displacement means there's going to be a switch. There's going to be two compounds, and basically the metals are going to switch places. There have to be two compounds, though, not an element by itself this time. Here you have a compound, here you have a compound, and if you notice, it's AX on this side, on the left side, but it's AY on the other side. It's BY on the left, and it's BX. So they basically switch partners. Okay, this is double displacement. There's a double switch. Not only does A kick out B, but B comes back here and takes A's place. Okay, they both switch places. Let's look at some examples here. Here we've got the metal potassium and the metal lead. And you'll notice it's the potassium that is in a compound with the iodine, but over here it's the lead that is in a compound with the iodine. Here the lead is with the nitrate, but over here it's the potassium with the nitrate. So basically the potassium and the lead switch places. It's a double displacement. They both
switch places, and they basically are going to form new compounds with the other nonmetal. Okay. Here's an example. Iron and hydrogen are going to switch places. Iron now is going to be with the chlorine, and the hydrogen is going to be with the sulfur. Okay. This is an example of, and we'll talk about this a lot when we get to acids and bases. This is an acid and a base. HCl, that's hydrochloric acid. NaOH, that's sodium hydroxide. The hydrogen is going to come in here and kick out the sodium, and the sodium is going to go over there with the chlorine. That's going to form sodium chloride and water. Water, you say? Yeah, there's a H with the OH. This is H with the OH is basically water. That's water. Okay? All right, the last type that we need to talk about is combustion. Combustion is something when it burns, okay? Something burning in the presence of oxygen. So if you were to light hydrogen, if you were to burn hydrogen in the presence of oxygen, you would create water. This is hydrogen and oxygen creating water, okay? Now, one thing I want you to recognize always is this. If you see what is called a hydrocarbon is a molecule that has carbon and hydrogen in it. Only carbon and hydrogen. Here is a hydrocarbon. When a hydrocarbon burns in the presence of oxygen, it will always produce carbon dioxide and water. I want you to know that. You need to know a hydrocarbon. This is a hydrocarbon. Hydrogen and carbon, hydrocarbon, burning in the presence of oxygen. Oxygen is always diatomic. Will always produce carbon dioxide and water. You need to know these products when you burn a hydrocarbon with oxygen. Okay? All right. This activity series, we are going to not cover that section. We are going to cover that later on when we get to electrochemistry. Okay? So just hold off on 8.3. You don't need to worry about 8.3 right now. All right? As I said, we'll mention that later on when we get to the activity series in talking about the electrochemistry. Okay? All right, that basically concludes Chapter 8. You just are responsible for 8.1 and 8.3. 8.1 and 8.3. And I will make another video that goes over these review questions for you so that you can be looking for that, and that'll help you answer these questions. Okay? All right, let me know if you have any concerns or comments or questions or you need some help. I'm always here to help. Have a good one and keep up the good work. All right?